So this lecture on circuitry begins with some terms that were covered in chapters 15 and 16, which we're not covering in AP Physics 1. It's kind of like the backstory you have to know to understand circuitry. So look, this term electric potential, the symbol for it is V, and what it is it's energy per charge. Now what do we measure energy in? Joule. We measure charge in coulomb. That's new for seconds. We haven't talked about coulomb. Last week I mentioned it. Okay, joule per coulomb. What do we call joule per coulomb? That is a volt. A joule per coulomb is a volt. It's energy per charge. So if you're talking about a single point, you're referring to the electric potential at that point. Now what we really care about is what we call potential difference. Get it? It's the difference between 2 points. It's the change of the electric potential. If the electric potential changes, you call that a potential difference. Another name for potential difference is voltage, and the symbol is delta V. Makes sense because delta is change. So if you change the electric potential, that's referred to as voltage, also called potential difference. Okay, so Ohm's law right here. We talked about Ohm's law last week. The delta V is the potential difference. When you're using Ohm's law, delta V is voltage or potential difference. Now, look at this diagram here. This right here is grounding, that little symbol there. Wherever you see that in a circuit diagram, that's telling you that that point right there has an electric potential of 0 volts. Now, your volts will only change if you cross a battery or a resistor. Now, when you cross a battery with the current, in the direction of current, and let me just briefly mention, how do we define current flow? Current flow is always positive charge motion. So if you have a positive charge in the wire right here, little positive dude, is he going to go towards the positive plate of the battery or away? Away. So the current goes around like this, so I is the symbol for current. Current comes down like this through the resistor. Current comes back around like this. So if you cross a battery in the direction of current, the volts will go up. We call that a voltage increase. So if this is a 12-volt battery, see, 12 volt, that is the delta V for the battery, the voltage of the battery. So this negative terminal would be 0, right? Because right here is 0. Now we cross the battery. What's the other side of the battery going to be? 12 volts. Now what does this mean, guys? All this means, what does 0 volts mean? It means 0 joules of energy for every coulomb. What does 12 volts mean? It means 12 joules of energy for every coulomb. Right? So as 1 coulomb, so say you have 1 coulomb of charge, here comes 1 coulomb of charge. How much energy does he have on this side of the battery? 0. Then he crosses the battery. If it's 1 coulomb, how much energy does he gain as he goes across the battery? 12 joules. So all circuitry is, when it really comes down to it, it's this cycle. As charges go through the battery, they gain energy. When they go through the resistor, they release energy. So let's look at that part. How many volts do we have right here? Let me ask you this. How many volts are right here? 12, right? Because nothing happened from here to here, 12 volts. The only time your volts will change is when you cross a battery or cross a resistor. Now, so how many volts over here? 12. Now, how many volts down here? 0, right? Because that's 0 right there. Now, look, as the current goes across the resistor, it's going from 12 volts to 0 volts. Again, 12 volts just means 12 joules of energy per coulomb, and then 0 volts is 0 joules of energy per coulomb. Right? So we have potential difference. If you're talking about a single point, like bam, right here at that point, the electric potential is 12 volts. How about from this point to this point? Now you're talking what? If you're talking about from one point to another point, that is called the what? The potential difference, which is the voltage. And this is what we care about mostly. You're not going to really care about the electric potential at a single point. You're going to care about the change between 2 points. And then when will it change? When will volts change? Whenever you cross a battery or a resistor. Now, let's get down to business here. first thing. So today we're going to talk about resistors in series. Tomorrow we're going to talk about resistors in parallel. So the first thing you have to recognize is why these two resistors here, why would those be considered series? The answer is there's no branching in the circuit. The current comes out of the battery like this, positive charge motion. Current comes out like this, goes up like that, boom. Current goes through this resistor, boom. Current goes through that resistor. Did the current branch? Was there any splitting? Nope. That's the defining characteristic of series. Real quickly, I want to show you what tomorrow is going to be. Tomorrow, we're going to look at resistors in parallel. So here's a battery. Boom. Here's two resistors. Now these resistors are said to be in parallel because look what happens. So here's the battery. Current comes out of the battery. Boom, like this. Now what happens to that current when it reaches this point right here? It what? It splits. You know, a common analogy with current is water through a pipe. Just pretend this is water through a pipe, like you're setting up a sprinkler system. Anybody ever done that? You set up a sprinkler system in your yard, so you got water flowing, water flowing, water flowing. Bam, it hits this point. What happens to that water flow? It splits. It bifurcates. Okay? That is parallel. These resistors would be parallel. So let's focus on series for today. Tomorrow we're going to do parallel. Now, first thing, how to simplify two or more resistors that are in series. It's real easy. You guys know the word equivalent? That's what this EQ right here is. That EQ is I'm a bad speller. Did I spell that right? Yes. Equivalent. EQ for equivalent. Guys, if you have two $5 bills, two $5 bills would be equivalent to a $10 bill. How about two $10 bills? $20. It's the same exact logic here. Same exact logic. If you have a 2 ohm and a 3 ohm, oh, and look at, real quick, I never mentioned this unit here, this ohm, this horseshoe, 2 ohm, just make note of this, that's equivalent, an ohm is a volt per amp. Okay, so what it's saying is, if you say that this is 2 ohm resistor, you're saying you need to have 2 volts to get 1 amp. Right? You got to have 2 volts across that 2 ohm resistor to get 1 amp. What would 3 ohm mean? 3 ohm is what? 3 ohm means you need to have 3 volts to get 1 amp. It's 3 volts per amp. Right? So as the resistance goes up, you need more voltage to get 1 amp of current. All right? So that's the ohm, which you're going to use. Now, we got a 2 ohm and a 3 ohm. What's that going to simplify to? A 5 ohm. So look, this picture on the left is the original circuit. This picture on the right is the simplified circuit. All this is over here on the right, this is a simplified picture of the original circuit. But they're identical, dude. They're identical to each other. Just the one on the right is simplified. And by the way, guess what the key to circuitry is? Key to circuitry is simplified pictures. Believe me, you. Believe you, me? Which one is it? Believe me. No. Believe me, you. Yes. Hey, believe you, me. Simplified pictures. All right. So now you know how to simplify. Okay. Now the next thing I want to talk about is, so now that we've talked about simplifying circuits here, current, when you have resistors in series, current is the same. Now here's what I'm telling you. What I'm saying is this. So see these two resistors, they're in series. The current in the 2 ohm resistor and the current in the 3 ohm, these currents are what? The same. Now a common mistake is kids look at this, especially if you don't really know circuitry, you look at this and you're like, your first thought may be that this resistor has less current because the resistance is larger, right? I've heard that like 1,000 times. Spaldo, isn't this a larger resistance, so shouldn't it have less current? Well, your logic is kind of correct, but here's the thing I want to teach you. Where does a resistor affect the current? The answer is everywhere. Look, this 3 ohm resistor right here, where does this resistor affect the current? Does it affect the current only right there? Or does it affect the current here, 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 even inside the battery, here? It affects it where? Everywhere. A resistor in a circuit does not just affect the current right there. It affects the current everywhere. Here, and I have a good analogy for you. A frequent analogy for current is water through a pipe. So see my giant pipe right here? Okay, look. So imagine you got water flowing through this, right? And what I'm going to do is I'm going to add some resistance by stuffing in some tissue paper. So imagine I take some tissue paper here, right? And I take some tissue paper and I stuff the tissue paper inside here, okay, just to clog it up a little bit. Could water still get through this? Yeah, water could still get through it, but did I add some resistance? Yeah, dude, and the resistance is right here, right where I'm holding the pipe. Now, the resistance is there, but will this resistance affect the current here? How about down here? Yeah, so my point is simply what? Where does a resistance affect the current? Everywhere. Okay, so the end result, when you have resistors in series, the current in this guy and the current in this guy, it's the same current. How about the current over here? So this guy has current. Is this current going to be the same or different as these currents? Same. Why does that make sense? Well, think about it. What is this picture on the right? It's the same thing as the picture on the left, only simplified. So if you can find the current, over here in the simplified picture, then you found the current in the original picture. So let's do this. Okay? Next thing we're going to do is we're going to find the current. Now, remember we talked about voltage. If this is a 20-volt battery, the easiest way to do this is make the negative plate 0, the positive plate 20. Because what happens when the current, so here comes the current, right? Positive charges are cruising through. What happens when the current goes through the battery? Are they going to gain volts or lose volts? Gain. That's just a fancy way of saying, remember, what is a volt? A volt is a what? It's joules per coulomb. It's energy per charge. So as the current goes through the battery, it's going to gain volts. Now, dudes, did I have to do 0 and 20? I could have done 100 and 120. Because look, at the end of the day, what's important? The thing that's important is the what? The change, the difference, right? Okay, so let's just go 0 and 20. It's easy. 0 and 20. Okay, so how many volts would I have right here? 20. How many volts would I have up here? 20. Let's do the other side. How many volts over here? 0. How many volts right here? 0. So notice, as the current goes through the battery, it's a voltage gain. As the current goes through the resistor, it's a voltage loss. What is the voltage loss? What's the delta V across this resistor right here? It's got to be 20, because look, 20 on the left, 0 on the right. So the delta V is 20 volts, technically negative, right? But don't just absolute value this. It's technically negative because you're losing volts. Now, to find this current, all we got to do is bring out which equation? The most commonly used equation in all of electricity and magnetism, Ohm's law, delta V equals IR. So I is delta V over R. Okay, so how many volts across this resistor? 20. How many ohms? What's the resistance? 5. And remember, so ohm, but remember what an ohm was? What's an ohm? Volt per amp. So this gives us 4 amps, right? Because the volts cancel, right? 5 ohms means you're going to get, you need 5 volts for every amp. So if you have 20 volts across a 5 ohm, that's going to give you 4 amps. So what we now know, the current here is what? 4 amps. So what's the current over here? 4 amps. What's the current here? 4 amps. You got it, dude. Hey, Have I told you that every year kids are like, dude, circuitry's awesome. Every year kids like it. I'm not just lying to you. I'm being for real. Every year kids are like, dude, circuitry's kind of fun. Okay, so that's 4 amps. Now, final thing, look at idea number 2. When you have resistors in series, voltage is not the same. So what this means, the delta V across this guy. So let's figure that out. And the delta V across this guy. Let's figure that out. Are these going to be the same voltages or different? Different. Okay, what's the delta V across this 2 ohm? Well, how do we figure it out? Back to Ohm's law. Delta V equals IR. Do we have the current through this resistor? Yes. Do we have the resistance? Yes. What's 4 times 2? 8. Okay, now, this guy. Do we have the current through this guy? Yes. Do we have the resistance? Yes. That's 12 volts. Notice the voltage is not the same, right? Now, of course, when would the voltage be the same? The voltage across these guys would be the same only if the resistors were equal. You know, if they're like 2 ohm and 2 ohm or 3 ohm and 3 ohm. But now, what do you notice about 8 and 12? What do you notice about 8 and 12? They add up to 20. Because going back to this idea, look, if this is a 20-volt battery, 0 volt, 20 volts. And again, did it have to be 0 and 20? No. Unless it's grounded. If they show you grounding, if they're like, ding, ding, if they ground the circuit, what does grounding mean? They're telling you what? 0, right? So we got 0 and 20. So how many volts up here? 20. How about right there? 0. So across from here to there, what's the delta V across the whole thing? 20. But is that going to be 10 and 10? You know, in this case here, it's 8 and 12, but they add up to 20. So final question, and then we're done here. What's the electric potential at this point in the middle? Remember, electric potential is at a single point. So we have 20 here. That's the electric potential here, right? 0 there. What has to be the electric potential here? So start right here. So we start at 20. What happens across this first resistor? We lose 8. So this must be what? 12 right there. Then we go across the next resistor. What happens there? And we're back to 0, which is where it should be, right? In general, the voltage gain in the battery must equal the voltage lost in the resistors. Voltage gain in the battery must equal voltage lost in the resistors. It's this cycle of energy gain, energy loss, energy gain, energy loss, right? And the energy gain and the energy loss, it's going to be expressed, you know, typically you say voltage gain, voltage loss, but voltage is just energy per charge. It's energy per coulomb. I think this has been a pretty good discussion. Let's end it now.